Recording in progress. That sounds so efficient. All right, so we're going to take a look in section 5.2. The very specific title is in 5.2, binomial probability distributions. Binomial. All right, so a little bit about the binomial type of things before I give you some real hard and fast definition. The binomial probability distribution is for discrete random variables, and it includes repeated trials. So we'll be doing the same thing over and over and over again. And each one of those trials will have but two possible outcomes. This is why we call it a quote unquote binomial distribution. We have a random variable. It's the x because that's the letter we like. It is the number of occurrences of a particular outcome. So there's only two possible outcomes. So we're going to be looking at the number of occurrences of either one of the outcomes or the other of the outcomes. All right. So let me give you the actual definition. And this is the technical definition. Some of it is easily understood, very straightforward. Other parts of it are a little bit more subtle. So let's see. A binomial probability distribution is produced by the following procedure. So there are four requirements. If whatever it is you are doing does not contain or have these four requirements, then whatever it is you're looking at will not be a binomial distribution. Not that it doesn't have value or interest, but it just won't be that. So there are, as I say, four requirements. The first is that we have a fixed number of trials. In other words, we decide before we even begin how many times we will flip the coin, how many times we make a random guess, how many times we repeat whatever it is we're doing. Each one of the outcomes of those trials must be independent. This is a little bit more difficult for students to apprehend and get a handle on. And that is because the notion of independence is really truly fuzzy. It's really just coming into view for you guys. But basically, I'll remind you, the outcome of one trial cannot affect the outcome of another trial. So the trials must be independent. If you flip a coin 10 times, you flip it an 11th time, that flip doesn't care what happened the first 10 flips. Each trial must have two outcomes. We like to call those two outcomes success and failure, although you can't put a lot of emphasis on success being something good, possibly, and failure being something bad. The idea is you've got two outcomes, and you need to distinguish between the two of them. You call one success and one failure. Also, as you work through all of those trials, however many there are, the probabilities must remain constant. They must not fluctuate from trial to trial. You flip the same coin over and over and over and over again, the probability of a head or a tail remains the same for each of those flips. So that's the technical definition of a probability distribution. Students are very, very good, that would be you guys, very, very good at working with the number of trials and determining if there's two outcomes. You have a much harder time determining if something is independent or if probabilities remain constant. It's just the way it is at this stage of your education. So let's keep that in mind, and let me give you some notation, and then I'll offer up some examples. So we like the letter S for success and the letter F for failure. The probability of success is a value given by little p, and the probability of failure is given by little q. and Q is equal to 1 minus P. At the end of the day, S and F, probability, excuse me, success and failure are complementary events. They span the probability space and they just one or the other. Now, we're going to let the number n stand for the fixed number of trials. Hello, question? We're going to let the letter X stand for a specific number of successes in those n trials. As I noted up here, little p is the probability of success in any one trial. Little q, probability of failure in any one trial. P of x, there's our probability notation. This is the probability of exactly x successes in those n trials. So that's the notation I use. I tend to mess around with S and F depending on what it is we are working with. If we're flipping coins, it might be H and T, heads and tails. If we're guessing, it might be correct and incorrect for a question on an exam. So I'm not wedded to S and F. The notions are well defined within each of the problems we look at. So let me give you an example of what we mean here. We are going to start by flipping a fair coin 10 times. And we're going to let X equal the number of heads that we might see in those 10 flips. Now, the question is this situation, is that situation a binomial probability distribution appropriate approach? Well, do I have a fixed number of trials? Yes, I do, because we're going to flip our coin 10 times. Are the events independent? Yes. My coin does not remember. My coin tosses are always independent. Do I have two outcomes? Yes. Heads and tails. My coins do not land on the edge. Finally, do we have constant probabilities? Yes, I'm flipping the same coin over and over and over again. The probability for a head or the probability for a tail will not change between flips in some magical fashion. So let's take a look at that. In terms of our notation, n is equal to 10. Now, there are some instances in this course where students really must know, absolutely know particular values by heart. You should know that when you flip a fair coin, the probability of a head, in this case, that's my success, is 1 out of 2, because that's how fair coins work. Therefore, you also know the probability of a tail is also 1 out of 2. That's your failure. Now, therefore, we know that the p, little p, is 1/2, and the little q is also 1/2. This is a little relationship that we use an awful lot. P and q have to add up to 1. And that's exactly what I see. 1/2 plus 1/2 gives me 1. P plus Q's got to be equal to 1. But most importantly, I often must calculate Q. I will be given P, but I've got to actually calculate and find Q. So we're going to flip a fair coin 10 times. X is the number of heads. So yes, this is a binomial probability distribution procedure that matches the 4 requirements. In terms of notation, there it is. That's what we have. Let me give you another example. Apparently, 85% of adults out there, at least in America, have heard of Twitter. So In terms of selecting an adult who has heard of Twitter, the probability P is 0.85. Is that enough for me to determine what the probability of Q, the probability of a person not having heard of Twitter might be? Yes, it is. And because I know this, I also know this. Those are the people that have never heard of Twitter. Now, when we go out and we sample in terms of these kinds of surveys, we'll take a person here and then a person there. And that person, once we select them, we actually keep them out of the pool. We don't want to double sample. So there can be a real problem with the notion of dependent events. However, well, in the best statistical fashion, we honestly kind of ignore it. In other words, when my sample size or the number of trials is less than or equal to 5% of the population size, I have or assume independent events. And I gotta love this. Our book calls it the cumbersome calculation rule. Oh, it's too hard. I need an easier way. Easy now. All right. I mean, maybe I'm putting a little bit too much emphasis on that, but we really do use this cumbersome calculation rule all the time. And the reason for that is because, yes, there would be a difference, but the difference happens so many decimal places out that in terms of what we're interested in terms of things that really affect our lives, it just doesn't play. For example, in terms of a nationwide poll, we might select 1,000 people, but that's 1,000 people out of something like 320 million, or maybe it's 360 million. I always forget. It's a hell of a lot of people, and the size of the sample is super small. So sure, there would be some flux, but not enough for us to get ourselves worried about. Now, we're going to look at the formula. I really do like looking at this formula because it enables us to use some of the stuff that we've been talking about already. I also think it's important to understand that when we turn things over to Mr. Calculator, we understand what the calculator is at least attempting to do. If you understand well enough, sometimes you get to pick up on error that has occurred. Maybe you punched in 21 instead of 12 or something of that nature. In any case, we have a formula. So when we've got a binomial distribution, the formula for exactly X successes in N trials, that probability is given by the probability of X. And then you've got this weird factorial thing right here, n factorial divided by n minus x factorial. You got your probability of success raised to the number of successes you're interested in, the probability of Q raised to the total number of trials minus the number of interesting successes. It's important to remember that X, your random variable, can take on any value from 0 through 1 all the way up through n. You can flip a coin 10 times and get 10 heads in a row, though that would be unlikely. I will also point out that this guy here can be more easily written as n choose X using our combinations. We really don't care the order in which people come into our surveys, for example, or the order we're worried about the coins coming into the counting of the flips. That doesn't matter at all. So it's n combinations. So in some sense, order is not important when it comes to developing these types of data sets. Now, when I put this up on the board in a face-to-face class, I take a look at people's eyes, and honestly, it's a little fun. I enjoy it. Students don't like it, they cringe. Some of them even look like they might throw up. But I can't see any of you. No, you're all hiding behind your names and whatnot. Don't worry, I'm not going to ask you to disrobe. Um, what I will point out, though, is I'm going to use this formula one time and one time only in my very next example. And as soon as I use this formula one time, I'm going to go ahead and switch to using my calculator. And the very first thing I'm going to do is validate the formula with the calculator, or actually validate the calculator from the formula. So that's the formula. Let me get rid of that. So as I say, for just one time, we're going to flip a coin 10 times. We're going to let X equal the number of heads. So I want to find the probability of exactly 4 heads in those 10 flips. I know how coins work, so I know P and I know Q. When I plug that into the formula, I've got this 10 choose 4 times, there's P raised to the probability, raised to the number of successes. And then I've got the Q, and there's Q raised to the number of N minus X successes. I've got a value here. I'm going to switch over to Mr. Calculator, and we're going to take a look at the keystrokes here. And again, this is really not the appropriate way, I think, to do this type of problem for the most part. It's fine for us to look at it now, but you really want to learn a better approach in general. It's just much more portable. So let me share my screen. There's my calculator. All right, so what I need to do is I need to put in that particular formula. So the way that works is I can type in the 10. I go to math, to probability, find the combination number, and then I'll put in we're exactly 4 successes out of the 10 flips. I've got a little arrow. I don't want my next calculation to be down there where the 4 is. It's got to be applied to whatever the combination returns. So we're going to multiply that by 0.5. And then I use my caret key. And this is where I type in the 4. And again, I don't want my calculation to continue up in the exponent position. So my right arrow brings me down to the line with everyone else, and I'll multiply it by another 0.5, another caret, and another 10 minus 4. Most of the time, students find it easier to do that little bit of calculation in your head. Most people can handle 10 minus 4, even in a stressful test situation. So there is the formula in all its glory. I'll blow on it once for luck and hit enter. And there we go, 0.205078125. Now, let me go ahead and stop my sharing. Come back over here. There's a 0.20507 in the change. We want to round to 3 significant digits. So I take the first 3 non-zero, well, starting with the first non-zero digit, and then I have to look at the next one out to tell me what to do with that 3rd digit, or the 5 there. So at that point, I've got my rounded version, and the problem is complete. Now, as I say, this really is not the best way to do this problem. I'm going to introduce you to a new place on your calculator. I don't believe we've been here before. I might have done it once just off the cuff, but I don't think I've really been here before. So when we're working with a binomial distribution and we're finding exactly X successes in the end trials, I use a special key called distribution, which is abbreviated disturb. No, it doesn't stand for disturbed, distribution. And under that distribution menu, I have binomial PDF, and it's got an open parentheses there. I need to supply something. I need to supply end trials. I need to supply P, the probability of success in any one trial, and I need to supply the X value, the exact number of successes of interest. I'm going to do this twice because the keystrokes are a bit different depending on how your calculator might be working. So let me go ahead and get rid of this for now. Let me bring this over again. Just a little bit different, but pretty much the same. So we got the same coin flip. And again, we're looking for exactly 4 heads. So in terms of what my calculator will ask for, I'll give it 10. I'll give it 1/2. It's smart enough to figure out Q. It knows the 1 minus P thing. And the X value in question. There's the result I should get. So let me come back to Mr. Calculator. There you are. Hello. All right, let me get rid of that. So the distribution key is right up above the vars key. You see it there, DISTR, right up above the vars in blue. So second distribution, and we actually use a fair number of things on this menu. So there's my binomial PDF. So there you see it with the parenthesis and everything. I'll hit enter. And I have Mr. Wizard turned on, so I can plug in the number of trials, 10. By the way, I can use either 1/2 or 0.5. I'm going to type in 1/2, and I'll tell you why. Sometimes that probability would be a fraction developed from, say, 1/3, or a decimal place from 1/3. Most of you would probably put in a 0.3. If you put in a fraction, the calculator will round for you, which is why I like the fractions. The X value in question is 4. And then the last command is a little puzzling. It says paste. So to paste, you just hit enter, and it puts it into sort of the old-fashioned format. And you're going to see why this is important in a moment. I'll hit enter. And there's a 0.205078125, and I'm sure there's more decimal places back there. So do I get the same value? Yes. And this is a much more painless way of going about doing this. Let me redo this calculation with my stat wizard in the off position. All right, so this time when I go to my distribution menu and I pick up my probability distribution function, that's what PDS stands for. That's what I get. So this is where I plug in the 10. Got to hit it with the comma. The 1/2. Got to hit it with the comma. The 4. And then depending on what else is going around in the vicinity, you really need to close that off. Sometimes you can get away with it, sometimes you can't. Excuse me. Blow on it once for luck. Then you hit enter, and there it is. I'm going to turn my stat wizard back on. I find the stat wizard works pretty well with my distributions, and it makes entering the data just a bit easier. All right. So let me stop my sharing. And there we go. So that is really how I expect these problems to be done. Now, what else goes on with this process? Well, there are some things where it may not be clear that you actually have a binomial distribution type of problem in front of you. We're going to make random guesses on a 5-question quiz. And that 5-question quiz is a multiple choice. So you take these all the time in my course. Usually for my multiple choice, it give you a choice of 5 distinctly different results, unless I made a typo. And you'd pick one of those 5. One of the 5 would be right. 4 out of the 5 would be wrong. So we want to find the probability of exactly 2 correct results. So I'm going to do that on my calculator. Probability of exactly 2. I'll even put the rounded version down there. But before I do that, I need to get ready. I need to determine what n is, what p is, and what x is. We're going to guess on 5 questions. So we have 5 times of guessing, 5 trials. Now, what is the probability of being right on any one question? On any one question, you're going to be guessing and picking 1 out of 5 possible results. So the probability of guessing correctly is 1 out of 5. And by the way, that means Q is 4 out of 5. We're not going to need it. Our calculator will find it just fine, but I do like to point that out. Exactly 2 correct guesses. So with that ready to go, I can now come back and actually answer the question. Let me share my screen. There you are. Clear you out. So, second distribution. PDF. Exactly. We have this time 5 trials. 1 divided by 5 is the probability of success in any one trial. And we want to get 2 out of the 5 questions right when we guess. So that probability, 0.2048. All right. So that's it. 0.2048. I need 3 significant digits. The 8 tells me what to do with the 4, so 0.205. That wraps up that particular problem. You got to look for the word exactly to make sure you're using the correct tool. They don't mess around, honestly, too much with the language for this type of problem. Exactly is pretty much exactly, but in any case, there we go. Now, this can get messy. There's another type of problem that we need to work with these binomial distributions. Very many times we are not concerned with exactly so many successes. For example, if you're guessing on a quiz, you want to guess enough to get at least, say, a C on the quiz. If you guess more that are even more and get a better grade, that'll make you even happier. So we refer to this as the sum of many. And these are the types of questions where we ask, what is the probability of at least, at most, more than, or less than those X successes in N trials? We have a tool for that also. Binomial CDF. CDF stands for cumulative distribution function. And that is the tool that we use to handle this type of problem. How do those type of problems look? And this is where it gets a little bit tricky. So let me set the stage and walk you through how this process works. Then I need to run through a second process. And that's really the one that is the most involved of all of these. So we've got 20 randomly selected births. We're going to let X equal the number of girls in those 20 births. We're going to assume that the probability of girls and boys is equal for any one birth. It's really slightly biased, but I'm not going to worry about that. We never do. So here's the question. What is, in those 20 births, what is the probability of less than 10 girls? That means that we are interested in births. When we're looking at those 20 births, we're interested if we see no girls, or one girl perhaps, or two, or all the way out to 9, because 9 is the last whole number that is less than 10. Notice my use of the word or. Use of the word or means one thing and one thing only. It means the addition rule. Yes, that addition rule from 4.2. Unfortunately for us, that's what's required. Fortunately for us, our calculator can work with this quite easily. It's also not as hard as you might think. So the probability that the 20 births I work in contain somewhere between 0 and 9 girls is really found by calculating the probability of 0 girls in those 20 births, 1 in those 20, 2 in those 20, all the way out to 9, and summing those probabilities. These are mutually exclusive events, so I don't have to worry about a double count as we had to in some of those problems in 4.2. So here's the way it works. Very much like we did before, I have to supply n equals 20, the number of trials. The probability of success in any one trial, and I need to convey the upper X. So when I convey that upper X, that means the calculator will run through this calculation right here. That's what this will do for us when I convey this. And this is with that cumulative distribution function. I'm going to go over the keystrokes in just a minute. I have an answer right there. Let me see if it's correct. It'll be embarrassing if I get a different number, but I'll probably be able to live with it. So let me share. Goodbye, go away. All right, so I go back to my distributions. CDF, cumulative, sum of many. I have, how many trials did I say? Oh, I had 20 trials this time. 1 out of 2 is the probability of a girl in any 20 births. The X value in question is 9, because we're interested in what? Less than 10. And it's sometimes it's that vocabulary, that less than, that gets to people. Paste that in. I'm going to point out that the numbers we put in and the way we put them in have the exact same sort of order: trials, probability, value. So 0.41190 and change is the result. So let me stop my sharing. Come back over here. And I see the 0.4119 and 0. When I round that to 3 significant digits, I get a 0.412. So there we go. That's the most basic type. The ones of these sums of many, the ones are for less than and at most. Less than is strictly less than. Less than or equal to is the at most. So the straightforward approach works good when that's the situation. But that's not always the situation. The way my tool works is for the cumulative distribution function, it always starts at 0, always, and goes up to a value that you input. But it always starts at 0 and it counts up to that particular value of interest. Now, that's a problem on some particular types of questions because we can't address it in a very direct fashion. So we have a 10-question multiple choice quiz. We're going to make random guesses on that quiz. That 10-question multiple choice, each question has 5 possibilities, just like my quizzes. And we want to find the probability of at least 3 correct when we guess randomly. So, in terms of my notation, we're looking for the probability of 3 less than or equal to x, less than or equal to 10. Those are all the successes or correct guesses. 3 correct, perhaps, or maybe you were lucky enough to get 4 correct, or 5 or 6, or maybe you're lucky to guess them all correctly. Unlikely, but possible. So this is a problem. Why is this a problem? Because no matter what, my calculator starts at p of 0 plus. That's why that's a problem. Now, the way to address this, and I make sure I include problems like these on our quizzes and our exams, because this is how these problems are dealt with in the real world. We need the use of the complement. So, my set A, if you will, 3 up through 10 correct guesses. That's my event A. I need a complementary event. That complementary event, A bar, are all the things that are not in A. The possibility of getting them all wrong, getting 1 right, or perhaps 2 right. And I need to remember my rule for complements. So, the way I set this up is I set it up as 1 minus the probability of the complement. See the complement there? Now, for the complement, I've got to make sure I use the correct results. I have 10 questions, 5 possibilities for each. So P is 1 out of 5, 0, 1, or 2, because we're counting up. And there we have it. Now, that is the result that we have. Let me come over to my calculator. And I'm going to point out that you can go ahead and this is how you want to do it, by the way. You want to do it in a single calculation. So literally 1 minus. Then you come and you pick up your distribution. So 10 trials, 1 out of 5 chance of being right on any one, 2 or fewer successes, so 0 or 1 or 2 correct guesses. That gets pasted in. And I get a 0.3222 and change. Before I run back over to my screen, I'm going to run through the calculation one more time with the stat wizard off. So 1 minus, this time when I pick up my cumulative distribution function, that's what I see. So 10, comma, 1 divided by 5, comma, 2. And then I close up that parenthesis. Blow it out once for luck. And there we go. So regardless of how your calculator might be set up, that's really the way to do this type of calculation. You really don't want to try to write this down or try to do, I should say, try to do this separate and then write it down and then subtract it from 1. That does not work very well. That's honestly, that is really a step below where we want to be in terms of ownership of our technology. So let me stop my share there. And I'll note that the probability of at least 3 correct guesses on this type of situation, 0.3222 and change. When I round that to 3 significant digits, 0.322. And there we go. So we've taken a look at a couple of things tonight. I want to just do one little bit of summary here. I want to summarize these tools and issues. So we have, in terms of a summary, I gave you an introduction to a binomial probability distribution. That was the first thing we took a look at. You've got a list of 4 things to check, some easy, some not so easy. Then we have the single success, where we have exactly X successes in those N trials, and we use the excuse me, that's a D. I said B. Binomial PDF. I'm going to leave the parenthesis off now because I really want to focus our attention on the exactly and the PDF. Then we have the sum of many successes. The language there was a little bit different. I will actually list it. At least, at most, less than, more than. So that was our sum of many. And depending on how things were set up, well, we use the cumulative distribution function for the sum of many. That's CDF. And again, it's this language right here. And I'm not saying people can even be more creative than that. But there we go. Sometimes we had to use the complement, but I'll leave that off the simple summary here. In any case, that there is your first half, if you will, of 5.2. Tomorrow, I am not going to be here. I will have to reschedule those office hours, and I'll reach out to the group tomorrow with more detail there. But I will finish up the second half of 5.2 on Thursday. And the time honestly might actually change for the Thursday office hours. In any case, there we go. So let me stop my recording.